Hello, my name is Aparna. This video is regarding a linear regression problem and the approach I have used to solve it. Linear regression is one of the most widely used modeling techniques in predictive analytics. To solve any data analytics problem, I use cross-industry process for data mining, abbreviated as CRISP-DM. I start by developing a business understanding around the problem, which in this case is to understand the factors affecting the pricing of cars and to find out which variables or features are significant in predicting the price of a car. The data provided consists of a list of car models along with their features and prices. For this problem, I have not sourced data other than what has been provided. To get a better understanding, I take a look at the first few rows, the summary and the structure of the data. Using the data dictionary if provided, I get a sense of what each column represents. I identify the predictors and the response variable. I check if there is any unique identifier for each record. I make a note of all the observations made as a part of data understanding. In the data provided, there are 26 variables, out of which price is the response variable and all other predictors. Car ID is the unique identifier for each record. As a part of data preparation, I start with data cleaning. I check for missing values, null values and NA values and impute them accordingly after thorough analysis. I remove duplicated records. I treat outliers, if any, on a case-by-case basis. I check and remove spelling errors, if any. I bring all the string values to the same case. I derive new variables as and when required and convert the variables to correct data type. In the data provided, there were no duplicate records, there were no null or NA values, there were no outliers. There were some spelling errors which were corrected. I also extracted the company name of the car from a column which contained both the company name as well as the model name of the car. Next, I start with univariate exploratory data analysis. I plot histograms of categorical variables and check the summary statistics of numeric variables. I then move on to bivariate analysis. I make correlation plot of all the numeric variables to understand which variables are positively correlated and which of them are negatively correlated. I make scatter plots of numeric predictor variables with respect to response variable to understand their relationship. I make box plots of categorical predictor variables with respect to response variable. I make a note of all the observations from the exploratory data analysis. Next, I create dummy variables to convert categorical variables to numeric variables. This is done because linear regression modeling can only take numeric variables. Before modeling, I divide the dataset into training and testing data. I take 70% of random samples as training data for modeling and reserve the remaining 30% as testing data for model evaluation. I begin data modeling by creating the first model with all the variables of training data. I note down the results of the first model. Then, to drop the least significant variables, I use stepwise selection method as part of variable selection process. Here, I have used the step AIC function of the mass library to remove insignificant variables. AIC in the step AIC function stands for Akaike Information Criteria, which allows to pick a good model with less number of variables. I use the variables from the result of the stepwise selection method to create a second model. I note down the R-square and the adjusted R-square values of the second model and take a look at the changes of these values with respect to the first model. I check for the multi-collinearity in the second model by using the VIF function of the car library. I take a note of significant and insignificant variables on the basis of their p-values and multi-collinearity. Insignificant variables are the ones with high VIF values and high p-values. I create a third model by removing the insignificant variables in the second model. I note down the results from the third model and compare them with the results of the second model. I then again check for multi-collinearity of the third model. For every model, insignificant variables are identified on the basis of the p-value and multi-collinearity. And new models are created by only including significant variables from the previous models. This process of creating new models is repeated till such a point that all the variables of the final model have multi-collinearity below the set threshold limit and the corresponding p-values are very, very low. The final model should also not have too many variables. For every model created, the R-square and the adjusted R-square values are compared with the previous model. This is done to ensure there is no sudden drop in these set values. The sudden drop indicates that a significant variable has been removed. For car price prediction, I created 13 models. The final model was the 13th model with only 11 variables, and all of them had low p-values and low multi-collinearity. The R-square and the adjusted R-square of the final model were 0.9599 and 0.9559 respectively. After data modeling, the next step is model evaluation. I use the final model and the test data set to predict the price of the cars in the test data set. I calculate the correlation between the prices that were predicted using the final model and the actual prices that were there in the test data set. The square of the correlation value gives the R-square value. This R-square value should be close to the R-square value of the final model. The R-square value that has been calculated comes out to be 0.83. This means the final model can explain 83% variation of the actual price of the test data around its mean. I make a density plot between the actual and predicted price to get a visual representation. I also plot the predicted price with respect to the actual price as a scatter plot. I then plot the residuals of the final model to ensure that it is a normal distribution. In conclusion, the final model created using linear regression to predict car prices explains 83% variability. The car company, engine size, drive wheel and aspiration play a key role in predicting the price of cars. Other factors like engine location, fuel type and fuel system can help determine the groups in which the car should be priced.